In this video, we're looking at an LR circuit. Now, it may not look like there's a resistor there, but I'm including an internal resistance of this inductor coil of 105 ohms. And we're told the specs on this coil. It has 3,000 turns. It has a length of 5.1 centimeters, an average diameter of 1.8 centimeters. We're going to use those specs to compute the inductance of the coil. Then, given the inductance and the resistance, we should be able to figure out the half-life for the current as it grows in this circuit after we close the switch. And then finally, we're going to look at what happens in the long run if we leave that switch closed. So first, we need the self-inductance of this coil. And I'll post a link to the video where this was first discussed. It turns out the formula is mu naught n squared A over L, where mu naught is the permeability of free space, n is the number of turns in the coil, A is the cross-sectional area of those turns, and little l is the length of the coil. So we plug in the permeability of free space, that's 4 pi times 10 to the negative 7. The number of turns, that's 3,000. And then I need the cross-sectional area of each of these loops. Well, that's pi r squared if I know the average radius. I was given the average diameter, and I may as well use that directly. The area of a circle with a given diameter is 1/4 pi diameter squared. My diameter is 0.0158 meters, converting those centimeters to meters. And then our length is 5.1 centimeters, that's 0.051 meters. When I run the numbers on this, to 3 significant digits, I get 0.0435 henries. And it's common to convert a result like this to millihenries, 43.5 millihenries. Next, I want the time for the current to rise to half its maximum value. In other words, I want the half-life for this circuit. And I'll post a link to the video where this was derived. The half-life is given by tau natural log 2, where that tau is a time constant given by L over R for the circuit. We plug in our inductance of 0.0435, and then the coil itself has resistance that was given as 105 ohms. And this gives me 2.87 times 10 to the negative 4 seconds. Or I could write that as 0.287 milliseconds. Finally, we want to compute the maximum current after this circuit is allowed to run for a long time. So if you recall the way that current increases in an LR circuit, it's given by an exponential function. It's asymptotic to some maximum value. So this is what we mean by a long time, long enough to reach that maximum value. And the key concept behind this is that after a long period of time of applying this direct current voltage, the current is no longer changing in the circuit. So the inductor is no longer resisting changes in current, and you don't have to worry about the back EMF created by that inductor. In other words, the inductor becomes transparent in this circuit. So after we wait for a sufficiently long period of time, the circuit is totally equivalent to this one resistor circuit, sort of the simplest possible circuit. We use Ohm's law to figure out what the current is in this circuit, and I is V over R. I'm applying 4.75 volts over a resistance of 105 ohms. And when I run the numbers on this, I get 0.0452 amps. And again, it looks better if we switch to milliamps. We get 45.2 milliamps, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.